So our next talk is presented by Florian, and he's going to introduce us to Ferrocene project, which talks about the super cool Rust topic.
Well, the super cool Rust topic because it's the Rust compiler. As there was a suggestion to do karaoke, if you ever go to a Rust conference, there's a ask for the traditional karaoke session. There's one after every. So hello, I'm Florian. I'm managing director of a company called Ferrosystems based in Berlin. I've previously been with the Rust Foundation and the Rust project, both as a core team and community team member. And I've been training Rust since 2015. I'm doing this for 10 years now. That's quite a bit. And as I said, as I'm from Berlin, if there's one wish I have as a Rustation currently for the German industry is I wish we stopped talking about where do we find Rust developers, because Europe is actually a Rust country and Germany in particular. So it's actually here, and I think we should leverage that. So just very quickly about Ferrosystems, it was formed 2018 by a couple of Rust project members because they found the need, there needs to be a company to help companies adopt Rust. We're mainly a training and maintenance company. We are co-maintaining not only the Rust compiler, but also the Rust IDE toolkit, Rust Analyzer, an embedded flashing toolkit called Knurling, BindGen, parts of the infrastructure. If you ever used Rust, you're touching systems that we maintain. And Ferrocene is one of those projects which is actually bringing Rust into safety critical, qualifying the Rust compiler. And because I always get the question, we're in the last weeks of that. So it's pretty much around the corner that we have a TCL3 qualified Rust compiler. And in the meantime, we're partnering with other major projects, like, for example, bringing Rust into Google Android. And so much about that. So I want to talk quickly about what even is Ferrocene, what are the tools that we're using to validate it. This thing called not rocket science, what is that as a principle, how we execute all of these rules and approaches, and the experiences that we had along the way. So first of all, what is Ferrocene? At the simplest level, it's a qualification of the Rust compiler, Rust-C. And for that, Ferrocene is a complete downstream in the open source sense of the main Rust toolchain that you can find on github.com/rustlang/rust. So it imports the whole toolchain regularly, further validates it, and in the end qualifies it currently for ISO 26262 and IEC 61508. It is also, and that's the long detour, a language specification effort. Because one of the long complaints about Rust was Rust does not have a specification. Now it turns out that here in this industry, we need requirements, and for programming language, it just happens to be that the requirements document is a language specification. So the first half year of that project was actually writing a complete specification for Rust 168 currently. That's the version that we're qualifying. That's from January. It is also a product that provides long-term supported Rust. Currently, the Rust project does only provide support for the last 6 weeks for the currently released compiler. Ferrocene provides support for longer. And the last thing, it's fully open source based. So we're using open source tools and particularly methodologies derived from the Rust project. And these are the things that I want to introduce you a little to. So I need to introduce you to a few basics. The Rust project has something that it calls a train model. And this is actually the train model for Ferrocene. The Rust project itself runs a simpler one. So it has multiple levels of releases. And regularly, some of those releases are promoted down into higher trains. So for example, we do release every night a version, the current version of the compiler, if it is releasable, which it should. We have something called pre-rolling, which is a version that is intended for later being released. Upstream calls that beta. And at some point, we promote that to a release. This is what you see as rolling. 159, 160. Rust version numbers get high quickly because, well, we're releasing every 6 weeks, and we've been doing that since 2015. And for the qualification, we take a step up. So we're shipping all of these to customers. And for qualification, we take one step up. Regularly, we take one of those releases qualified and also release that as a qualified version with safety manuals, signed safety manuals and everything. The other thing where we differ, Rust has an idea, and you can find something on the Rust project which is called the target tier policy of, well, this idea of target tiers. Target tiers describe the level of support that a target gets. A big misconception is that does not necessarily describe the quality, only by proxy. Tier 1, and this is what we'll be mostly talking about here, are fully supported targets, which means any bug found will block release or even merging of any patches into the Rust compiler. And they're fully automated. They need full automated testing. Also, they need a support team in the upstream project, so on and so forth. We have tier 2, which are projects that are supported and shipped with the compiler, or targets that are supported and shipped with the compiler, but may not be automatically tested. One of those examples is, for example, Google Android. The Rust compiler team itself does not test things on Android, which also plays into what I was saying. That does not mean that it's a low quality target. It's just the upstream project does not do any kind of quality assurance on it. Tier 3 is code is in the repository, but there's no guarantees beyond that. You can build the compiler your own, may work, may not, still random quality. And why is that important? For example, ARC65 unknown none, bare metal ARC65 targets are something that upstream doesn't test. It's tier 2, but we test it. For us, it's tier 1. So that's also a difference between the two projects, between the upstream and the downstream. And the other thing, Rust practices since, as I said, I've been doing Rust for a decade, and this rule predates me, is the not rocket science rule of software engineering, which is automatically maintain a repository of code that always passes all tests. Any patch, like any patch on the mainline is green. And plain CI is not enough for that. And the other ethos that we combine with that, I go into how we achieve that in a second. And the last ethos that comes out of Rust comes out of Mozilla research, and Mozilla research, even as a research department, said, what can't be released isn't software. So the Rust compiler, even the early alpha versions, was something that always could build a release binary and could be released on macOS, Windows, Linux, and they had to regularly exercise that every 2 months. Doing that regularly for 3 to 4 years before even releasing Rust 1.0 built a lot of practice that actually gave us the head start that we needed once we actually brought that language to the world. And that means every build is a release. So the whole test machinery for the Rust project is completely built towards actually building release binaries. A release is, in the end, just copying them to the right place in the release infrastructure. So here's a couple of tools used. I'm focused on just 2 of them, but the main tools that we're using Sphinx for all kinds of documentation, the Python documentation framework, together with some plugins for that. We're using a tool called BOSNG for automation. There's a star besides that because recently GitHub has released a feature called merge queues, which is behaving quite similar to BOSNG, but not quite. And that means that BOSNG is nowadays deprecated. It's still useful, can still be used, but that's something I think I should disclose here for anyone who is investigating that. And we're using Sigstore for document signing. So we even have the document signing built into the CI system. And a tool built by the FSFE here in Berlin called Reuse for licensing and SBOM concerns. I'm going to focus on the first 2. The second 2, if anyone's interested, please meet us around the hall. And yeah, and we're using GitHub as a code platform and Circle CI as the build platform. GitHub, particularly for the reason that the upstream project already uses GitHub. So for reusing all of the automation that it already built. It's just natural to also use it. So what does Bors do? Bors implements a pretty interesting process. It maintains a queue of changes or pull requests to the compiler that are ready to be merged, which means they've been reviewed. And then it serializes them for testing. I have a small picture on why that makes sense in a second. It serializes them for testing, so only one of those tests runs at a time. It is also an automation of all operations on the repository. So no one clicks the merge button. We instruct Bors, this is ready for merging, do everything that should be done for merging. So all of these small processes actually get implemented. They're made simple and then implemented. It does all the important bookkeeping, for example, tracking who reviewed and who authored a change. And then it signals back, for example, on failures or on success towards the platform. So here's an example. This is Pietro. Pietro is over there, our infrastructure engineer. So when Pietro says, okay, I'll approve of this pull request, it's the first step. Actually approving towards GitHub. They now have review features, approving towards GitHub. Hey, that's fine. And then instructing Bors to merge. Then our bot will actually comment, hey, yep, I'm doing my work now, and come back later. Okay, the build succeeded. Thank you. Will then merge into the main line or into the branch that was merged towards, and also do the cleanup, delete that branch. So how does it do that? What it does, instead of merging to the main line and then running tests, it takes the main line, forks it, merges all changes on top of it, runs the test and merges them back. And if you look at the first picture, this is the reason why that also means that there should only be one test running at once, because fixes could contradict each other or changes could contradict each other. So if we're testing those under the assumption that they don't contradict at the same time in parallel, we could end up with a main line that is broken by combination. So what it instead does, it only runs one of those at once. So we can put multiple changes in the queue, 6, 7, 8, 9, 10, and both will just work overnight and see if they're all mergeable, and we can come back next morning and figure out, well, okay, half of that worked, the other half didn't. The Rust compiler builds for an hour or something like that, or a little bit less on some targets. So that's also very useful. And what it also does, it uses the commit message to then document what is done. For those that are Git nerds, we actually do merges. And those merges document, hey, what was forked, when was it merged, and particularly who reviewed and who authored something. So we see two of our employees here, Vakrel and Pietro. Pietro reviewed Vakrel, and the other way around for the other pull request. And it's also being put into the Git metadata. So these co-authored by, for example, are actually things that Git can then pick up, and which are also displayed, for example, on GitHub's interfaces. What that gives us is a straightforward path to improving this. After we've got all of this process down, a straightforward path to improving the quality of that tool is more testing. And so what we do instead of the upstream project is we also consider all the qualification material and the tracing of the qualification material part of the software test. So for every change, we also build it and we release it, and that is also never allowed to break. So no unaccounted tests, no tests without requirements. And for us, as I said, that meant writing a language specification, because language specifications are quite dense documents where almost every sentence is a requirement. We've gone as far as taking inspiration from the ADA specification. The ADA specification has a thing called legality rules, and actually numbers every sentence in the specification, and so that it's clearly addressable. So we can trace down to this test addresses 0.7.1:1 in the specification. Usually we work on sections. And out of that, we built a plain normal traceability matrix The most important part being this unique link over there that says the tests to the right are actually the compiler tests that all refer to section 7.1 in the spec where constants are described. And as I said, there's no such thing as a partial build. So this is one of our build runs. The most important things here is the branch that you see there. This is the staging branch that Bors will use and reuse for doing its work. It's never manually managed. This is the one that Bors works on, and if it's successful, actually merges back. And the other one that I highlighted in red, that's the part where we're actually building the traceability matrix and also making sure that all our traceability is working fine. And again, that we never lose track either of changes in the specification or of changes in the compiler, because the compiler between, just to be clear on the scale of this problem, the compiler between 2 releases has around 1,600 changes in 6 weeks. And that's the speed that we need to follow and that we shouldn't lose track of. And we're also using the platform that we're using a lot for automation. Don't be confused that a lot of these tests have been failing of these pull requests, because otherwise they would automatically land in the closed part. They're still open and have a red X because they need to be cared for. The other ones are already closed. The one thing that's interesting about that picture is GitHub gives you a lot of ability to annotate a lot of the things that you have in there. So for example, every pull request here gets tags, whether they are, for example, caused by automation or caused by humans, things like that. And also, for example, all of these have a tag whether this change also needs to be backported. This one applies to the current mainline, but for example, some of those would need to be backported to 168, 170, or something like that. And we actually encode that in this tagging for, well, later again, tooling to pick it up. And that's been a run through the change management that we employ there. A lot of it basically being an extension of what the Rust project already does. So to come to the experience part of this, I think one of the things that we should care about is major open source projects nowadays are already using very strong processes informally. So what we basically been doing, we have formalized the process that the Rust project has been informally following anyways and have strengthened that. When you're downstreaming a project out of the open source community, whatever that may be, it's been very useful for us to play along with the rules that it already has. Any kind of divergence or, hey, this is not the practice that we would like to use actually costs a ton. So playing along those rules or trying to change them upstream, so we have a couple of patches upstream where we say, this makes work easier for us, is quite useful. And the other thing that we found is we found a project for basically everything. You can use Sigstore for signing, you can use extending Sphinx is okay, easy, I would say. And tuning it to the way that we need it on our own terms in our own house has been part of giving us our velocity. Simplifying all of the rules without any kind of branches, like all of these are dead simple rules that can be easily applied by a bot. And every time we find something that is so easy to apply that it can be done in a short shell script, we do it in a short shell script instead to make sure that we never fail at applying it. And automating and using our platform's API, in that case, GitHub, has been totally worth it, like with any minute spent. And that brings me to the last thing. As an old CI engineer, there's no such thing as setting up automation too early. As I said, these principles have been applied for a decade now, and the Rust project has also taken them over from previous projects. And it takes time to have them well sorted, rolling easily, running smoothly. Like in the beginning, all of this feels like a behemoth. Getting people used to that takes months. So on a project of that scale, that has been something that I've been also been caring about when I was part of Rust core. Like the experience that an organization builds with that is also part of that tooling, like the humans that use the tooling. And that's why the tooling should be there early and be refined over quite some time. Yeah, so that's my short run through what we do. And I'm happy to take questions.
Okay, now it should be on. So thank you very much for our presentation. So I think it's very interesting the approach that you are following for certification, really about traceability to really build up evidence that everything was done according to the best practices for that. So for more specific to Rust, so we are building another Eclipse project called Zeno completely in Rust. And you know that in Rust, you've got your code and tons of external dependencies. So when it comes to certifications, right? So how can we can deal with such complexity regarding that it's not only your code that you need to certify, but the Rust ecosystem kind of tends towards external dependencies in one way or the other, including also the standard library, which is not part of the core language features per se.
It's a good question. So first of all, thanks for building Zeno and for using async.std, which I've also been a maintainer of. So the whole dependency discussion, I think, is one I would really like to have a conversation with like this is one that I can have opinions on, but I cannot answer because this is kind of like encroaching on what should an ecosystem do, and it's really, really bad for one entity, even if it's systems or even the Rust project to try to encroach on an ecosystem. There's multiple perspectives of that. So, for example, if we take async.std as async.std for reference is an event reactor that works much like the standard library, but every kind of I/O interface is actually asynchronous and uses Rust asynchronicity features. Almost all dependencies of async.std are actually under maintenance of async.std. And so the question about a dependency is always, is there, like, it's less how many libraries are in there, but how many parties are maintaining those libraries. And that can differ from classic, if you look at NPM, where this is even more extreme. In the JavaScript ecosystem, you have something like React, where it's basically impossible to figure out who to even call for this subsection of the framework. While in Rust, you do have, for example, larger projects that end up using multiple libraries for the reason that a library boundary in Rust is also a strong module boundary. It acts as both. So it is quite common that projects would actually separate themselves into multiple libraries. From a certification perspective, that can also have advantages because the scope of review becomes smaller. In the end, I think we end up in a situation where we should think about how do we declare better who maintains a library, what are the guarantees around it, and build actually a language around how does this library evolve? Will this stay at 1.0 always? Will it be, and the Rust ecosystem has all of these kind of things. So for example, there's a parser library in Rust that has the policy of every major version change, we change our API completely. It's called NOM. NOM1, NOM2, NOM3, NOM4 are different libraries. And even the importance of even understanding what their policy is and what the guarantees they want to give us is already a hard thing. So I don't have a strong answer to that, except this conversation needs to happen. And the other thing is coming from ecosystems where we don't have structured library management, that's essentially being had implicitly by, for example, having libraries that ship with 100 functions that you only use 2 of, for the reason that you have no better ability to ship them in a different way.
One of the elements is, I mean, call it certification, is demonstrated proven use. So it's also about the community to prove if there are some safety artifacts in the library. If that's well documented, at least we would certify it and would say, look, I mean, if you have a database, it's okay, I make a tick in the box. So that's where I think the community can help. I mean, building also safety inside the system. It takes an effort to document your safety gaps somehow in order that they can be ticked off. It's one of the options you can probably go for in such a system, even open source environment. But you can talk to me later if you want.